How do you solve a problem like a Spectre? I mean, really solve it in a way that doesn't kill performance and doesn't leave another similar bug there for tomorrow instead. The way we deal with this is we come up with a specific security policy that you need to obey called Strictness Ordering, and then we develop GhostMinion, a cache system that enforces this. But before that, let's take a little look at how side channel attacks really work. So what we've got here is an attack on the cache, which is usually a way that you exfiltrate information via a Spectre gadget to leak secrets you're not normally allowed access to. So in this example, the attacker primes the cache, then the victim is tricked into loading a secret that they didn't intend to, which is then indirected to so that the next load that happens, A of secret, is based on the value of that secret. So the address now leaks the secret by either evicting or not evicting this primed location. And that's a prime and probe. The other example is an evict and time, where rather than evicting data, you bring in data based on the secret address. Both are possible. And that's a side channel, but Spectre and Meltdown are speculative or transient side channel attacks. So the way that works is that we've got some code like we have here. This is a V1 gadget on the branch predictor. And let's say that to this code, we give the following inputs. X equals 928, so and so and so on, and the array size is 100. Well, clearly that's outside of the bounds, so this branch will never happen, right? And that's true in correct execution. But the branch predictor, having seen this code many times before, and every other time it was called, that was absolutely what happened, it was absolutely within those bounds, it will say yes. So that code really does get executed. And so our strange out-of-bounds access here does get forwarded through to this array2 of y. And there are many uses for this kind of attack. The main ones are either to escape a sandbox. So say if you're in a JavaScript or WebAssembly sandbox within a browser, or even a extended Berkeley packet filter sandbox inside the kernel, then you can escape out of that sandbox by escaping out of any bounds checking. And you can also leak secrets from other processes if you have inter-process communication. And the sort of intuitive thing that you would come up with to fix this is, okay, so we've misspeculated, so let's roll back all of that misspeculation. And in our example over here, what we have is our branch here was misspeculated, but we don't know that yet. So we keep executing these misspeculated instructions. We eventually discover the misspeculation, and this load here is the next valid instruction. So all of those are rolled back. So if we then wipe the cache, well, we certainly can't access it from this load here, right? Our clearing at the end of misspeculation, once we've restarted execution, will prevent us from learning anything past that point. But what about the load over there? Can we learn anything about any of the loads that happened here? See any of the cache state or anything else that leaks what happened in this misspeculation up here? Well, that's before it, isn't it? So surely not. Well, all of these are running on an out-of-order processor. Spectre is an attack on out-of-order processors. So all of these are in the pipeline at the same time. Even though those instructions up there will commit, and those instructions down here won't. Those will be part of the transient execution gadget. But actually, because they're in the pipeline at the same time, this load here will be able to see any of the effects of all of this, so there will still be a backwards in time cache side channel. Clearing on misspeculation won't be enough to stop you from seeing the bad things that happen that might break your security during speculation. So, is it ever safe to transmit the result of a misspeculated load? Is it ever safe to allow potentially incorrect values to propagate around, or is that always going to leak secrets? And to make matters worse, while we're executing these instructions, we don't know that they're misspeculated. By the time we know they're misspeculated, it's too late. They might have already transmitted secrets to parts that we care about. And the answer is yes. as long as the recipient can't commit anyway. And that sounds like it might be a useless observation, but actually it matters quite a lot. It makes the sorts of restrictions that you can put in place in terms of where data can be sent to, where data can impact in terms of timing. You can be far more permissive than just waiting until it's non-speculative. And to do that, we come up with this ordering called strictness ordering. Now, this is trying to capture the idea very precisely of instructions that don't commit should never be visible to instructions that do. And so the definition is, let X and Y denote executed instructions. Under strictness ordering, Y can strictly observe X, so X is allowed to transmit to Y under strictness ordering, and therefore X can impact the execution time or cycle of any pipeline stage of Y, if commit of Y implies commit of X. So whenever Y commits, X commits. Or indeed, as it says down here, whenever X doesn't commit, Y doesn't either. So Y is allowed to see what X is doing regardless of what happens in the computation from that point onwards. A slightly simpler over-approximation that's very easy to implement in hardware, so that's what we use in this paper, is what we call temporal ordering, which is where under temporal ordering, Y temporally succeeds X, meaning X can impact the execution time of Y, if either X is guaranteed to commit, or already has, or X and Y are in sequence with each other, so X comes before Y in program order. The front end of a processor fetches instructions with increasing levels of speculation, but once that speculation stops holding, you then restart execution from a new point. So everything that's in the pipeline at that point will be more speculative than the last. And to show you what that means and the difference between them, what we have here is sort of increasing levels of permissiveness, where what we have on the right is unsafe. This is where everything is allowed to transmit to everything. What we have here is the strictness order. So this instruction here is allowed to see anything that came before it because it's more speculative than they are. It's also allowed to see everything up to this branch because all of these things here will commit whenever this does. So it's allowed to see that in the strictness order, but it's not allowed to see anything here because these might not commit even though this does. Temporal order is slightly more restrictive because everything after this instruction it can't see. It's no more safe, but it is easier to implement that the idea that this is more speculative than anything else before it, and that's all we need to know. And both are much less restrictive than blocking transmission of anything speculative. So this can't see the effects of any instructions here until they become non-speculative, and they're all guarded by this branch here. Okay, and how we translate that into hardware is via what we call this GhostMinion. So this is providing strictness ordering for the cache system. You technically need strictness ordering in an entire system, but we demonstrate it here on the cache system and show how that applies to other parts of the system later. And what we do is, to a first order approximation, we keep all speculative state inside this GhostMinion here, this attachment to the L1, and each core has one. And there is no speculative state in the L1, the L2, or the L3. So this is non-inclusive, non-exclusive with respect to the rest of the cache system. So we modify that and we place a variety of guarantees on it to actually enforce this strictness order. Just having it there isn't enough. You need to enforce various properties on this. We do that using these techniques called timestamping and leapfrogging. And we also have to provide that for the misstatus handling registers, where speculative memory accessors can propagate up these even though they can't affect any state here, so that they can request things from higher levels. So I've mentioned that just storing all speculative state inside a GhostMinion isn't enough to prevent these channels, because you still get backwards in time side channel if you can see things that other instructions have caused to happen inside that GhostMinion. So the restrictions that you have to have look like this. So what we've got up here is a read, and this read is at timestamp 21. So it isn't allowed to see this same read to the same location at timestamp 22. That's not allowed because this might be transient, whereas that might not be. So that isn't allowed to see this location here. Whereas this read at timestamp 28 to this location is allowed to see this value here at timestamp 27 because there's a timestamp order there. Whereas for filling, it's the opposite. On filling at timestamp 24, we aren't allowed to evict any data at timestamp 22 because that becomes visible to an instruction of a lower timestamp. Whereas we are allowed to evict something at timestamp 25 because that's higher, and we're also allowed to insert it in any free slots here. And actually, these free slots are very important. You need them there to avoid any sort of starvation, because otherwise, if your GhostMinion became clogged up with old data at a lower timestamp that had, say, committed, then the GhostMinion would be full and you wouldn't be able to add anything new to it. So once an instruction does commit, so we've got one here at timestamp 22, it is allowed to see this data here at timestamp 22 that it put in the cache, and it will then evict it to the L1. It will write back to the L1. That's the only way that data reaches the non-speculative cache hierarchy. No other speculative data is allowed to do that. And that makes a free slot so that we can start adding in new things at higher timestamps, because you can never evict anything of a lower timestamp with a speculative memory access. Now, even though all of the speculative state stays inside the GhostMinion, as I mentioned earlier, the memory accesses themselves, the request, will still have to propagate up the misstatus handling registers of the L1, L2, and L3 cache. And because of that, you then need to handle any contention effects because of that. So we've got a read here that's at timestamp 25. It can see these current read misses at the moment inside the misstatus handling registers because they're at a lower timestamp. What it can't do is see this. This must appear totally invisible to it because it's at a higher timestamp. So the way we implement that is we allow this load at timestamp 28 to greedily take this misstatus handling register. And then if this load comes along at a lower timestamp, it will then nudge it out of the way. It uses this technique called leapfrogging, where we put this load into here instead and delete this from the misstatus handling register. Therefore, that load must fail and then retry later once there is space in these misstatus handling registers. So that preserves the temporal order on this and thus the strictness order. I mean, that's all within a thread, but of course you also have between thread issues to worry about, and the basic idea is that different threads can't see the state in another GhostMinion. But we also have to have restrictions on the Coherency Protocol so that as the result of a GhostMinion, no Coherency Protocol changes happen in the non-speculative cache hierarchy. And basically, we steal this pretty much directly from Muon Trap, which is my previous work in the area, which we'll compare against later, which doesn't provide this temporal ordering property and therefore isn't protective against all attacks, only cross-domain attacks. The idea is that you get this sort of plausible deniability from the Coherency Protocol, that you don't need to know the state of anything in any other GhostMinion while still being able to keep coherency, because the GhostMinions are only allowed to bring in something coherently in a state that they would be allowed to without breaking anything else in a non-speculative cache. Though we've only talked about side channels within the cache so far, you also have to deal with side channels everywhere else. You need to make sure that Strictness Order is protected absolutely everywhere. And a key example of that is within the core. There were two famous attacks, one called Speculative Interference, one called Spectre Rewind, and that used the divider unit or non-pipelined functional units within the core to cause contention from future instructions to transmit backwards in time to older instructions, and we need to protect against that as well because it is a strictness order violation. Now, actually, that's quite easy to do. So you don't need to do anything for, say, a single cycle arithmetic logic unit other than prioritize earlier instructions if they're available in the same cycle. The same is true for a fully pipelined functional unit, because you won't block this for multiple cycles and you can make a decision every single cycle over which things are most eligible to use this, so there's no backwards in times channel. Whereas non-pipeline functional units, if we issue an instruction at cycle n, and then another instruction of a lower timestamp becomes available at n+1 that then can't issue, that's a problem. And the way we solve that in GhostMinion is we schedule these non-pipeline units in order with respect to themselves. So if there's an earlier divide in program order, you wait for that to finish before a later divide can finish. And if an earlier square root is still available to be scheduled, you don't schedule a later one until that one has been scheduled. Though there's no need for orderings anywhere else, you're just trying to prevent that congestion from being observable. And actually, in Gem 5 at least, that's a speed up rather than a slowdown. So the way that we implemented all of this was in Gem 5, the popular architecture simulator, and we ran it on ARC64. We simulated an out-of-order processor. This is the default out-of-order setup in Gem 5 that everyone else has been using for Spectre defenses. And we add to it ghost minions both on the data cache and the instruction cache next to each L1. And so here we compare the Geomeans of each technique, the full data is in the paper, against various other techniques in the literature. We've got my own previous work, muon trap, which muon trap is only a cross-domain protection, so it's only to protect between different processors. It doesn't have this concept of a strictness order, and it doesn't claim to. But we still do pretty well against it. We still beat it on Spec CPU 2006, where we only see a 2% overhead. We don't beat it on Parsec because it works very well for Parsec. Muon Trap puts its speculative region below the L1 as an L0 super fast cache. We can't do that because you evict lots of data from the Ghost Minion. You don't want it to be a cache for the L1 because you want it to always have free slots to provide that temporal order guarantee without exhaustion. We do beat muon trap once it's set up to empty the muon trap on misspeculation, which isn't enough to protect against these backwards in time attacks, but is enough to protect against the existing Spectre attacks. But we beat it quite considerably in performance there. In VisiSpec, we beat both its Spectre models and Future models, despite following the same threat model as in VisiSpec Future, that everything is speculative until it commits. Because the Coherency Protocol in GhostMinion is more optimized for the common case, but also it's far more resource efficient. In VisiSpec requires fully associative state, whereas because of the time guarding, GhostMinion can provide stricter guarantees. It can protect against things like speculative interference and Spectre rewind because of its time guarding, which also allows it to be set associative and not fully associative without giving the game away. And then it's quite a lot faster than STT on both of its Spectre and Future models because it's far less restrictive. Because of the strictness ordering / temporal ordering, you don't need to wait until everything becomes non-speculative to allow it to transmit between instructions that go from less speculative to more speculative. On the maximum, we see quite a similar story. The maximum for GhostMinion is a lot higher than its Geomean, particularly because of one workload in Spec CPU 2006, which is MCF. Where in MCF, it's quite reliant on data that is loaded in misspeculation, is then used effectively as a prefetch for the correct execution. And there's no safe way of doing that. So there's no way of avoiding that 30% overhead that we see in GhostMinion for that kind of workload. You just can't avoid it, and that's why everyone else is at least as high. Okay, so that's a brief introduction to GhostMinion and the strictness ordering. And what I want you to take away from this is the idea that, one, you really do need these quite precise guarantees to get hardware that really works and won't just be vulnerable to a slight modification of the attacks, but also that you can achieve these quite efficiently by using a precise but very generous ordering such as the strictness order. So thank you for listening, and if you have any questions either email me or ask at micro. Thank you.